This video is recorded to help my students to understand how to sketch the graph of a function. I will use a rational function f(x) equal 2x minus 5 over x plus 3 as an example. To sketch the graph of function, first we need to find the domain of the function, then we find the intercepts and plot them, then find the asymptotes and sketch them using dashed lines, then find the critical points and determine the local extrema. Then determine the intervals on which the function is increasing or decreasing. Then find the inflection points and plot them. Then determine the interval on which the function is concave up or concave down. After these 7 steps done, we have all the information we need to sketch the graph of the function. Finally, we sketch the graph by using smooth curves to connect the plotted points, ensure that domain, asymptotes, local extrema, increasing decrease property, and concavity property are reflected in the sketched graph. So let's start. The first step, we find the domain of the function. The example we use here is a rational function. To find the domain of the rational function, we only need to find all the x that make the denominator equal 0. Then the domain of the function is all real numbers except those x that make the denominator equal 0. So we will solve equation x plus 3 equals 0. We will solve this equation. Of course, this equation is very easy to solve. We know the solution is simply x equals -3. Now, after we solve this, then we know the domain is all real numbers except x equals -3. That means it is the interval from -infinity to -3 union -3 to positive infinity. That's the domain. So we finish the first step. Now, then we need to find the intercepts. There are x-intercepts and the y-intercepts. So let's first find the x-intercept. To find the x-intercept, we should let y equal 0, then solve for x. Okay. So for this problem, basically, we need to solve 2x minus 5 over x plus 3 equals 0. Since this rational is a fraction, so the fraction equals 0 only if and only if its numerator equals 0. So we actually will solve x minus 5 equals 0. This simply gives us x equals 5 over 2. So that's the x-intercept. Then we know that the graph will pass through the point 5 over 2, 0. Now, next step we find the y-intercept. To find the y-intercept, actually equivalent with evaluate function at x equals 0. So we actually calculate f0. F0 simply you just plug x equals 0 in fx function. If x equals 0, you know the numerator will be -5, denominator will be 3, so the answer will be -5 over 3. That's the x y-intercept. This means the graph will pass through point 0, -5/3, then the y-intercept. So we finished the first two steps. Now let's continue the third step. We need to find the asymptote of this function. So first, let's say vertical asymptote. In general, the rational function will have vertical asymptote. Vertical asymptote is just whatever you find in the first step, like x is not in the domain. So suppose a is not in the domain, then x equal a in general is a vertical asymptote. Okay, so in our case, it's simple since we found x equal -3 is not in the domain. So x equal -3 is the vertical asymptote. You also can check by this way. When x approach to -3, the function value approach to infinity. That's why x equal -3 is a vertical asymptote. Next, let's find a horizontal asymptote. Horizontal asymptote, in order to do that, we need to calculate the limit. Horizontal asymptote is we calculate the limit when x goes to infinity. What is the function's limit? Now, to calculate this limit, of course, you can divide x on the top and the bottom simultaneously. So the limit will become x will goes to infinity. Then we will have 2 minus 5/x as a numerator. Then we will have 1 plus 3/x as the denominator. So we need to calculate this limit. And this limit is simply equal the limit of the numerator, which will be 2, and the limit of the denominator, which will be 1, the quotient. So this limit is 2. So this limit is 2, it means the horizontal asymptote. So the horizontal asymptote is just y equal 2. Now we finish the third step. So the first step, we need to find the critical points and determine the local extrema. To find the critical points are those points that the first derivative will not exist or the first derivative equal 0. So we need to calculate the first derivative. So the first derivative of fx is you have to use the quotient rule. So the quotient rule is first take derivative to the numerator, then multiply denominator minus the numerator multiply the derivative of the denominator. This as the numerator divide the square of the denominator. That's the quotient rule. Then it's easy for us to figure out 2x minus 5 derivative is just 2. So you have 2 multiply x plus 3, and x plus 3 derivative is just 1. Okay. Now, the numerator, if after we do done the calculation, it's easy to say the numerator is just 11. So this is just 11 over x plus 3 squared. That's the first derivative. After we calculate this first derivative, we notice that this first derivative can never equal 0. Why? Because this is a fraction and its numerator is 11, can never be 0, so this first derivative can never be 0. And this first derivative will not exist at x equal negative 3, but x equal negative 3 is not in the domain of fx, so we don't worry about it. So as we said, we can make a conclusion says there is no solution for f derivative of x equals 0, then we can say, then we can conclude there is no critical point. Hence, there is no local extrema. Now, it has no local extrema. Now we need to determine on which interval the function is increasing and on which interval the function is decreasing. We know on the interval that the first derivative is positive, the function will be increasing, and the interval the first derivative is negative, the function will be decreasing. Now you notice the first derivative as 11 over x plus 3 squared is always positive. So this function should always increase on its domain. So we can make a conclusion since the function f derivative of x is always greater than 0, then we can, on the domain of fx, then we can conclusion, our conclusion is that the type is rather easier. We conclude that fx is increasing on each part of its domain. Why I say on each part? Since this domain divided by two parts by the point x equal negative 3, which is not in the domain. So fx is increasing on each part of this domain. That means fx is increasing from negative infinity to negative 3, that interval, and fx is also increasing on the interval from negative 3 to positive infinity. Next step, we need to find the inflection point. The inflection point are the points that second derivative not exist or second derivative equal 0. I mean, possibly, if a second derivative not exist at that point or the second derivative equal 0, that point are possibly inflection point. So we first need to calculate the second derivative. So the second derivative of fx is just the derivative of the first derivative. The first derivative, I rewrite it as this. Negative 2 power, okay? Then I take a derivative. Now, when we do this, this will give me negative 22 x plus 3 to the negative third power. This is just to use the power rule. Now, then I can rewrite this if you wish to, which is negative 2 over x plus 3 to the third power. Okay? Then the second derivative. Then we know this second derivative can never be 0. Again, this is a fraction and its numerator 2, negative 2, can never be 0. So this fraction value can never be 0. That means we do not have inflection point. Finally, we need to determine the interval on which the function is concave up or concave down. Now, we notice that when x is greater than negative 3, then the second derivative of f is always less, let's say x is greater than -3, x plus 3 is greater than 0. So second derivative is always less than 0, right? So the function is concave down. When x is less than -3, then we can say the second derivative is always greater than 0. And so the function is concave up. We determined it's concave up, concave down intervals. So the final step is we will sketch this graph by using smooth curves to connect the plotted point. Here is the graph. If you look at this graph, you can easily say from -infinity to -3, the function is concave up. Then from -3 to +infinity, the function is concave down. And y equal 2 is horizontal asymptote, and x equal -3 is vertical asymptote. And each interval of its domain, like from -infinity to -3, the function is increasing, and from -3 to +infinity, the function is also increasing. So we finish sketch this graph. If you have any questions, please give me an email.